So now I'd like to turn my attention to what happens if we have more than one source of a wave. How would those waves interfere? And while it is possible to think about transverse waves interfering, for instance, I can throw two pebbles into a pond and they will send out ripples from each of their sources and interfere with each other. I'm going to focus mostly on sound waves here. When you go into electricity and magnetism, since light is a transverse electromagnetic wave, you'll get to revisit that a bit at that point there. But let's think about sound waves. So the big idea here is that for me to have constructive interference, if I've got two sources of sound waves, so say I got a speaker here, and I've got myself another speaker here. Whoops. Yeah, I tried. If I'm going to be listening to it, say over here, if I'm going to have constructive interference, I need the two waves to be doing the same thing at the same time. So let's make this one here red. I mean, they'll literally both be sound waves, so it doesn't, it's not like they have different colors or anything. It's just to tell them apart. And let's make this one, blue. So here, we've got it so that at all points, crest meets crest, trough meets trough, and so we'll have constructive interference. So what's going to matter here is what's the difference in distance between, say, this speaker here, speaker number 1, we'll call this distance D1, and speaker number 2 over here, we'll call this distance here D2. Well, for me to have the two waves doing the same thing at the same time, you can see here I had one extra wave front here. Obviously, if I could somehow magically put both of the speakers on top of each other, that would work too. Or say if I had the two speakers side to side and I was standing in the middle, they would be equidistant. I could also say have these differ by 2 wavelengths or 3 or 4. In any event, if it differs by an integer number of wavelengths, we'll end up with crest always meeting crest, trough always meeting trough, and having constructive interference. So this means that delta D, so my D2 minus my D1 here, will be equal to m lambda. Now here, in addition to m being 1, 2, 3, or 4, 0 is also a possibility. So this is just saying as long as the difference in distance is 0 wavelengths, 1 wavelength, 2 wavelengths, 3 wavelengths, whatever, that's going to work out to be constructive interference. All right, but let's say we wanted instead destructive interference. What would that look like? So here to have destructive interference, the big idea is going to be that we will want the crest and the trough, the crest of one to match up with the trough of the other. So again, let's make this one here red. So looking something like that. And let's go ahead and make this one blue. So you see here, I'm always got crest meeting trough, and so they'll always cancel out, and I will end up with destructive interference. So What's going to give rise to that? Well, on inspection here, this distance here is one loop. So that's half a wavelength. So again, if we say that this distance here is d1, let's move that there so I've got a little more room. There we go. And we'll say that this distance here is d2. Well, this is half a wavelength. That's certainly one possibility. It would be delta D would be half a wavelength. Can we think of any other possibilities? Sure. 1.5 wavelengths would give me the same difference. I'd still have a crest, mean, a trough, or 2.5, or 3.5, or 4.5, or whatever. So the general case will be m plus a half lambda, where again, we're permitting m to be 0, 1, 2, 3, and so forth. Okay, let's do an example of this just to make things a little more concrete for us here. So let's say you're listening to a pair of speakers. Oops. And since this is physics land, you're listening to a beautiful rendition of the speakers playing a tuning fork playing concert A, which is 440 hertz. Now let's say that you are sitting some distance away from the left speaker for some reason. You're right in front of the left speaker. Let's make this distance 10 meters. Now, right here, unfortunately, your happiness turns to sadness when you realize that you can barely hear the concert A note, and you realize that you must be sitting at a destructive minimum. Let's assume that this is the first destructive minimum. And then let's figure out how far apart are these speakers to have created such a horrendous misfortune for you. Okay, so this distance here, from here to here, that's going to be our D1, which was our 10 meters. This distance here is D2, which we don't particularly know, but we do know that it is our D1 squared plus our x squared, take the square root. Now they gave us an important clue here. They said it was the first destructive minimum. So now you might be tempted to stick in a 1 for m, but don't. Look what the first possibility is. The first possibility is 0. So if this is the first destructive minimum, what we've got is that delta D, which is equal to D2 minus D1, is equal to m plus a half lambda, where m is 0 here. Well, we don't know the wavelength, but we were given the frequency. V equals f lambda, so lambda equals v over f. And since they didn't tell us anything different, we'll assume that it's the speed of sound at STP, 343 meters per second. All right, so following this thought through, we've got here D2 equals D1 squared plus, D2 is, the square root of D1 squared plus x squared. And we'll be subtracting our D1 here. And this will equal 1/2. And our lambda, we said was v over f. So that's going to work out to be v over 2f. Okay. So let's go ahead and do a little bit of algebra here and see if we can't suss out what our x is going to be. So square root of D1 squared plus x squared will equal D1 plus v over 2f. We can square both sides. We'll get d1 squared plus x squared equals d1 plus v over 2f squared. And let's see, we can subtract d1 squared from both sides. And then finally take the square root. And if you want to do more algebra to make it prettier, knock yourself right out. But this will be good enough to get us the answer. So let's go and take a look. This is going to be, we said that our D1 was 10 meters. So 10 meters plus 343 meters per second over 2 times 440 hertz squared minus 10 meters squared. Take the root. All right, so now remember, 1 over seconds and hertz are the same difference, so that cancels. And our units check. That's good. So let's go ahead and grind that through on the calculator, shall we? So we will have 10, 343, 2 divide, 440 divide, plus squared 10 squared minus square root 2.82 meters. So I mean, that seems like a plausible distance that our speakers could possibly be separated by beats. So again, this is a case of interference of 2 sources, but whereas last time we looked at 2 sources that had the same wavelength or frequency, here they don't. It'll show up most prominently when the difference in frequencies is rather small. However, my artistic ability is going to make it look bigger than that. So here, let's say we've got one wave like this. And then let's say we've got another wave with a frequency that's slightly lower, so a little longer wavelength. Now here I'm greatly exaggerating things. Yeah, something like that. Here I'm greatly exaggerating things because what I'm trying to show is that here we would be having constructive interference. So if I were to add the 2 waves together over here, the envelope that the waves would stay in would be rather large. Then right about here is where it would go destructive. So I was attempting to draw something that would look about like that. Didn't do too good of a job with that pink wave. Let's try it one more time. So I want it to match here. I want it to be upside down there. Match here. Okay, let's try it. Yeah, okay, something like that. So here I'll have crest meeting trough, and so the amplitude would cancel out. Over here I basically have crest meeting crest or trough meeting trough, and so the waves will mostly support each other through there. So the actual sum of the wave, if you follow it through, if you do the trig identities on it, you'll get that it looks like one of our ordinary mechanical waves, and it'll turn out the frequency will be in between the two. So this is our carrier wave here, and then the beat that we talk about is this variation in amplitude. So what you'll get, and I'll be demonstrating in a little bit when I drop in a video clip at the end, is you'll hear a warbling kind of sound. So the frequency of the note you hear, and you get all this from using your half angle and double angle relations from trig. The frequency of this carrier wave here will be the average of your two sources, but the frequency of the warbling, the one over the period from here to there, called the beat frequency, turns out to be the absolute value of the difference of the frequencies. So the biggest application of this that I'm aware of is for tuning musical instruments. So again, let's say you're tuning a piano. Again, concert A has been agreed to be 440 hertz, at least until a conductor says it's something different. Let's say you've got an out-of-tune piano. And when you strike the key, it makes a note of 446 hertz. When a piano tuner comes in to tune the piano, what they'll do is they'll take out a tuning fork at 440 hertz, strike it, and then play the matching key on the piano. The note that you'll hear while both the tuning fork and the piano are making a note will be the average of the two, or 443 hertz, but that's not what the tuner's listening to. The tuner's listening to the beat frequency. They're going to hear this wah, 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 superimposed on top of the note. That will be equal to the absolute value of 440 hertz minus 446 hertz, or 6 hertz. So that's a pretty substantial warble. It's going to be like whoa, 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 like that. And so the tuner's going, man, you should have called me in a lot sooner. They'll adjust the tension in the strings of the piano, and what they'll be listening for is for the beat frequency to start getting longer. So for instance, when they've got it down to 441 hertz, and their tuning fork is doing 440, the beat frequency will be 1 hertz, or you'll hear 1 warble per second. And so the warbling will go wah, 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 and so forth. So thank you for having made it all the way through this video series with me. I hope that you've picked up some stuff here, and hope that you had some fun. I hope that you got at least a little bit of a sense of wonder about the natural world around you, and I wish you the best as you continue your studies. So I will end this off with a video demonstration of this. In this video, I will have 2 speakers. The speaker on the left will be constantly set at concert A 440 hertz. For the speaker on the right, it'll start at 440, and then I will click it up in 1 hertz steps up to 444. Then drop it back down to 440 and click it down in 1 hertz steps down to 436. So what I want you to notice is when I go, say, from 440 to 441, you'll pick up that, you'll hear a warbling of about 1 cycle per second, 1 hertz. When I go to 442, you should hear it warbling twice as quickly, and so forth. You should also notice that as I work my way up to 444, if you've got a really sensitive ear, you should also notice that the overall pitch that you're hearing is going up slightly. That's because the oscillation frequency is the average, and they'll be dragging the average up. Similarly, when I go down to 436, you should notice that I'm dragging the average down, and the oscillation frequency will be going down a little bit as a result. But then you'll notice that the beat frequency will start Again, at 439 will be 1 hertz and work its way down to 436 will be 4 hertz. So best of luck in your future endeavors, and I will leave you with the beat demonstration. Have a good one.